very warm welcome to Michael Kissner. He's, what are you, Managing Director of Akhetonics? Yes, okay. And he will give us a brief some insights in quick and dirty PIC design. Welcome. Thank you.
Hi everyone. You might wonder what this title means. I hope it becomes clear throughout the talk. As a matter of fact, I actually changed somewhat the topic of the talk because of a paper that came out recently, but you will see in a minute. Maybe first, quick introduction, who we are, what we do, who I am. So we are Akhetonics, a Berlin-based startup, and we're working on all optical computing. So a computer that only uses photonics and no electronics. And we are a very small team at the moment, so we are an interdisciplinary team of 10, and which will become very important throughout the talk is it's half a photonics team and half a software development team. We were founded here in Berlin just 3 years ago and are supported through public funding sources and VCs, and of course our partners here, Optic BB, Berlin partner, so that's very nice that all of them are here as well. So this is the paper I just mentioned. You might have seen it if you're in the space of silicon photonics, but I want to highlight this paragraph down here, which is deep down in the paper, but it's super interesting because it talks about how photonics is designed. And it specifically mentions one thing, that too many want a custom process. So when customers go to a foundry, be it HHI, be it not IZM, but IHP or similar, you often as a customer want some tweaks, some customization, right? Which isn't actually great for the foundries. And the reason for that is that too many in photonics have been trained as, and I'm quoting the paper actually, trained as device people. Because everyone wants to create their own custom device, right? Everyone wants to create their own modulator, make it better, instead of using what is already in the PDK or what is freely available. And they tend to optimize their PICs by changing the process instead of changing their designs, which is also, not ideal. So, they're very hopeful that this trend is going away, that more and more people that are growing up in the photonics field, that are coming to the photonics field, are more of a, let's call them system level engineers, that think on a system level, that take existing components and integrate them. And this is actually what I want to structure the talk today about. How do we get there? How do we get from device people to system people? Because this is the only way we can scale photonics in the future. If everyone is just thinking about the device level, then we're just creating devices and nothing that can actually do anything interesting. So let's have a quick peek at electronics. How is it done in electronics? So in electronics, if you want to design even something complex like a CPU, right? You start and think about the system level, right? And it has become very accessible. So for example, you would think of a structure on how your CPU would work. It could be a RISC-V, it could be your own instruction set architecture. And then you write Verilog code or hardware description, like you write code. So in electronics, chip development, ASIC development, CPU development is software development. You're writing code, you're not placing individual components. And then you have a fully automated pipeline that pumps out the tape out. And finally, you get it fabricated, you get it back. These are examples from the Tiny tape out, which is you can think of it like an open source framework where you can create your own designs using an open source flow and open source PDK. And this has greatly contributed to the new trend in electronics that everything is open source, or at least the accessible parts are open source. You can think of Skywater, the PDK, it's open source, and you can create your own electronic chips, which has led to a lot more talent and adoption, right? Now everyone can design their own CPU in a few days and even get it fabricated through Tiny tape-out, for example, for quite a cheap price. And how does this work? Because they're not designing devices, they're designing systems. They're using something called standard cells, which I'll also show you later what that is, to design their systems. And they are one abstraction layer above the physics. So when they write their code, they don't even know what's happening in the electronics. They just know, okay, my CPU needs to be able to do arithmetic, it needs to be able to do control flow, etc., and that's it. And yeah, just a quick view on how that roughly works from an automated standpoint. So they start out with a system specification, architectural design, and then they start writing their code, and that's it. Everything that comes after, so the circuit design, the physical design, all of that is happening automatically through electronic design automation tools like by Synopsys, Cadence, Mentor, all these big guys. And the open source version of this is something called OpenLane. So the OpenLane project is exactly what I just showed you, this process, but as an open source tool. And the two interesting parts of it is first the first little box called RTL Synthesis, which is an open source tool called Yosys, which takes your code and compiles it to a netlist. And netlist is just a fancy word of how the building blocks fit together. And then it goes through the Open Road project, which is the automatic placing and routing of individual components on your electronic integrated circuit. And finally, you get your GDS2 file, you send to a fab, and you get your chip. All of this is automated. And this started with this famous book, 1980s. So we're talking about 44 years. This book came out by Mead and Conway, and it basically led to the way we think about electronics nowadays, VLSI, very large scale integration. And I should note that two things come from the foundry. You have the PDK, which is the process design kit, and you have the standard cell library. And this will become very important that these two things are very different. So what is the standard cell library? In photonics, we only know this PDK thing, right? What is the standard cell library? Well, it's a collection of elements or devices that are known to work in that process. For example, this is an XOR gate, so a logic gate in electronics, and you have all your needed parts there, so you know how it works, right? You have some spice model telling you how it functions, you have some, you might have a GDS file attached that even shows you what it looks like. That's very rare, of course. You won't get that with TSMC, for example, or similar. And you know exactly what kind of connectors it has. It is all standardized. It has a fixed width and fixed height so that it is easier to place them later, because when you place them, it's just a grid. So in electronics, everything is just these square blocks that have a fixed size, and then you know exactly where to do the routing, right? This is super trivial to route in electronics. Or not super trivial, but right? You simply have all your horizontal lanes in one layer, you have all your vertical lanes in another layer, and then yeah, you basically have no collisions, and it becomes very easy to route. And that is all thanks to this standard cell approach. So you have the standard cell library, you have the PDK, you have VLSI. You might have heard of these terms, of course, in photonics, but yeah, it's a pet peeve of mine that they are very much misused. Often the PDK is somewhat also the standard cell library, and when we talk to electronic foundries, they get confused when we say PDK, because to them that's just the specification of the chemical process in the fab and not the devices themselves. So it gets very confusing sometimes. And VLSI in electronics means the integration of millions of these standard cells. It doesn't mean just 10 or 100, it means millions. And sometimes you see in photonics, people, including us, so we always talk about photonic VLSI because it sounds cooler, but we are not integrating millions of these devices, of course. So how does the current PIC design and simulation landscape look like? So you have your Synopsys, Luceda, Photon Design, ANSYS, BPI Photonics, NATPET. These are just some examples. There are many more out there. And I just want you to look at these pictures real quick and notice that what they're designing is very, very compact. It's basically these tools are meant to design one standard cell. They're not meant to design systems. So I don't even want to say, these tools are great, right? These tools are really, really great. We use them, but they are not meant for system level design. These are great for designing devices. They are just too cumbersome for system level or VLSI integration. Imagine having millions of these blocks in there. Yeah, the system can't even handle these kinds of integration levels. So, what is actually missing for photonic VLSI? So, when we want to think about the future, right? Having like a photonic Moore's law scaling into the future. There are quite a few things missing. So, in the first, of course, we need some hardware description language that can describe photonics as a programming language. We need a way to unify how we design these cells or have a simulation model for these cells. And in electronics, you have, for example, the SPICE models for that. We need a software ecosystem that is able to do functional verification, right? To check, okay, what we're designing here along the way is tested on a software level, right? It makes sense because you can't really look at it anymore once it's a GDS file and then have a hope that you find the bugs. We need a generic set of standard cells. So we need some consolidation of what we believe are the fundamental building blocks of a photonic circuit. And of course, ideally we also have a fully automated route and place algorithm, something like OpenRoad. Now, I'm a big fan of open source, so it would be nice to have it all open source, but I can understand if that's not possible. This is also something new to electronics, so that's perfectly fine. So the first two, there are actually some attempts to do this. For example, one is the photonic Verilog A, so a photonic Verilog version for analog design by Numerical, and it has the ability to do compact models which could be comparable to what you have in SPICE in electronics. So let's say, okay, this is looking good. The photonic landscape is understanding this step. Now the software ecosystem around the functional verification, right? Yeah, we can actually take that from electronics. That's also perfectly fine. Now it gets a bit more complicated, the standard cells. We're not yet thinking about standard cells in photonics, but the community is getting closer. Some are, we'll see an example in a short second, but it's not a general approach. Most people are thinking about the waveguide, the bend, the multimode interferometer, but they're not thinking about the Mach-Center interferometer as an individual building block. And this is, for us, a huge problem. There's no automated place and route. I know a lot of tools, they have some hands-on kind of automation in this space, but there's no real full-scale place and route that simply takes your standard cells and places them all on a PIC, perfectly optimized, and you're ready to go and send it to the fab. So here I want to show one very cool example. So we really like what Thessaloniki is doing. We already saw that from Martin's talk earlier. These chips are actually fabricated here at HHI, and they follow this standard cell approach. So the guys from Windforce, from the University of Thessaloniki, they are thinking in standard cells. They see themselves as system engineers, right? So we have a standard cell for example, here, these are all mostly memory units, and they think of them as individual cells and simply place them ideally around the block. Of course, these are quite large, so you won't have hundreds or thousands of them, but it's nice that people are thinking about this approach. And just to compare the design flows, right? In photonics, you start out with your tool, you place your designs, interconnect whatever tool, right? And then you hook them up, simulate it, you get your results, and then you start placing them on your PIC. And then finally you can send them to your fab. This is semi-manual, often also referred to as co-design, right? Where the tool helps you somewhat, but you're still manually doing this process. And if you want to change something, for example, you messed up a certain length in a waveguide, you have to change that. That has effects on the rest of your system. So it's very resource intensive if you want to design that way. The ideal version, at least for us, is you simply write your code. You write what your system needs to be able to do. I want a wavelength filter for these and these wavelengths. Boom. And then you send it to some automated design pipeline, and it generates you a final tape out that you can send to a fab. So this is the ideal approach where you code and then you have an automated design pipeline. So we really strongly believe the future of design is coding. So you have to be sadly you have to learn to program. So you have to become a programmer. That's why our team is half developers and half physicists. Our developers are actually the ones designing the PICs, and our physicists are just simply telling them, okay, I want this, and then we send it off to the fab. We want to abstract away the physics and whatever is happening at the foundry. I don't want, this sounds a bit crass, but ideally we simply know what the standard cells do that the foundry provides, and then we can simply use them. That would be ideal for us. you need to learn about continuous integration, continuous development. So these are software type of development pipelines, because they allow you to create large systems on a chip. And this is what originally this talk was about: embrace Git. In software development, we use something called Git to manage how the code is, in a way, backed up, or how you can work collaboratively with your fellow teammates on one single PIC, for example. So I've been talking a lot about how we think it should be done, so I wanted to make a quick detour of a side project we have, which is called Connected PIC, which was created by one of our developers in his spare time. So it's a fun side project. It's nothing meant to be production use, and our benchmark for this tool was, okay, we take a software developer who has no idea about physics, we give him a 1-hour lecture on photonics and how our tool works, and he can start creating PICs using it. That was just what we thought would be a fun idea. So what we want is a simple, intuitive interface with a 5-minute learning curve, drag and drop design methodology, instant feedback, all that good stuff. What we don't want is to replace any professional tools. We don't want high complexity in this tool, and yeah, we want it to be open source and all that stuff. Now, this tool doesn't necessarily relate to what we were talking about earlier, because this does have the idea of a standard cell, but not on the scale of what we actually want. It is meant to be a stepping stone for us internally, how we think about standard cells. And the concept is very simple. So you have this grid of cells. You have a fixed place where you have your couplers, could be graded couplers, edge couplers, whatever. And then you start placing either waveguides, you place some couplers, etc. And then you have your Masender, and it's done. Very simple, very simple. And the way the cells work, you have your standardized cell size, you have a visual representation of what it does, you have maybe some slider to adjust the coupling of the cell. You have an S matrix for simulation purposes, and you have the ability to export it to a GDS file. And here are just some examples. You could think of anything. You could even think of full Masenders as a standard cell. You could think of AWGs and all that fun stuff. And yes. So this is what the tool actually looks like, right? We made it look like a game because we wanted it to be approachable also by students. And we think with Gen Z, the attention span is best kept with a gamified version. So this very simple tool here, you have a Masender, you have your ring resonator, and simulation is simply done by switching on the lights, and then boom, okay, you have 2 different wavelengths coming in. You can do some interference, you can do some simple, very simplistic, quantitative results from that. So now you're filtering out the blue light later. You can also change the length of the ring to, for example, filter out the red light. Yeah. You get the picture. It's very simple. That's how you use the tool. You can freely design stuff very fast, right? You can place your elements everywhere you want. It's meant to be simple. And the cool thing is you can export it to NASCAR, so then you would get something like this. And you see this NASCAR code looks very different to what you're usually used to in PIC design. It's just the standard cells everywhere and nothing special. Finally, when you create the GDS file, it looks like this, and you have your PIC design ready to go without ever having to think of where do I place my waveguide, where do I place that. It's very simple. Of course, you will fabricate this. It's a huge waste of space, but yeah, to get to know PIC design, I think this is a fun tool. It's open source, so feel free to try it out. Good. And some of the implementation details, who of you are wondering, we did not use Python because Python, it's very hard to create large-scale software tools with Python. So we use C# using the Godot engine. This is a regular game engine, so it's actually meant to be a game. It's fully source controlled using Git. It's fully, at the moment about 50% test coverage, so that we know that the tool works. It has a full CI/CD pipeline in GitHub Actions, and of course, free to download it and play around with it. It has an MIT license, so if you want to put your name on it, that's perfectly fine. we don't mind. It's meant to be for the academic crowd. So, some quick conclusions. This quick detour was just to show you that the standard cell approach isn't too complicated. It's not really a huge step forward. It's just a different way of how we think about PIC design, and something we hope will be the future of how we do system-level PIC design. And PIC design can be extremely accessible if we don't force the user to learn about all the physics, all the photonics, and just think about what does he actually want to do with the PIC. And designing PICs can be easy and fun. That's why this talk was originally, or is titled Quick and Dirty PIC Design, because you can just click around and design your PIC and you're done and happy. We should start focusing on the system level PIC design, and that's the main key message on this talk. And we should stop trying to reinvent the wheel with the foundries. We should stop asking them, hey, can you add 10 nanometer to your quantum well or something like that. All these weird kind of requests you sometimes see out there. And yeah, Connected PIC also has a big brother, which actually can do everything I just talked about, but that's just an in-house tool, sorry. I just wanted to show it. Good. So, thank you very much, and if you're interested in talking with us about defining the next generation of computers, the all-optical computers, I'm happy to do so, and thank you.